So we're in section 9.3, and what I want to do is kind of look back a little bit, describe what we've gone through, and then help you understand where we're at. So in chapter 8, we started hypothesis testing. And depending on the circumstances, we either tested one population proportion, one population mean, or one population standard deviation. Now, technically, there was two cases of the test for a population mean. That was when sigma was known. And somebody remind me, what's sigma? What sigma represent?
Standard deviation.
Standard deviation. Awesome, thank you. And then the other case where sigma was unknown. Now, basically, we didn't do this test at all. This would result in what's called a z-test, but it's really kind of hard to envision a circumstance in which you would know the standard deviation but not know the mean. That's just odd. So more likely, we'd end up with what's called a t-test over here, where we don't know what sigma is, but somehow we have a normal distribution that we can test, and it results in a t-test. So we had mean, standard deviation, and proportion, all for one sample. Then we moved over to chapter 9. In chapter 9, all of a sudden we started working with two populations. And we can test the same things. We can test two population proportions. That was section 9.1. We can test two population means. We did section 9.2 the other day. That was when we had independent means. So that is, we had two different samples. They didn't have anything to do with each other. So like the scores on your first exam and the scores from students in Dutchess Community College, which is where the author of this book teaches. So those would be independent. And today we're going to go to the dependent case. That is, we're going to have data that's related to itself. So even though we'll have two sets of data, somehow or another that data is going to be related. Now, an example would be, for instance, a before and after test, where you give somebody a test on their way into a course, find out how much you know, and a test on the way out of the course. Another one might be with, golf balls. If you wanted to show that your golf balls would go farther than somebody else's, you might give a bunch of professionals your golf ball to drive and then give them a competitor's ball to drive and see which one goes the farthest. So in that case, because you have the same golfer drive two different balls, even though you're getting two different measurements, those measurements aren't independent. The farther, the length that it goes is going to depend on the ability of the golfer. And certainly, I don't think they want to have me trying to drive these things, but how far I drive it the first time and how far I drive it the second time with a different brand, those are going to be related to each other. And that's going to result in a different type of test than what we did in section 9.2. So now, unfortunately for us, I don't have a nice fancy handout for section 9.3 that I did for section 9.2. Just couldn't get one together, sorry. But we still are going to do a hypothesis test for the difference of two means. It's just that we're going to have different assumptions that we're going to make here. So let me help you work your way through those assumptions. And before I even get that far, let's just look at the types of claims that we're going to do, the types of claims that we're going to test in this section. So we're going to test these types of claims. That mu1 equals mu2, that mu1 is less than or equal to mu2, or that mu1 is greater than or equal to mu2. Now, so far, that seems like the same kind of test that we did back in section 9.2. And you're right, it is the same kind of test. Except this time, we're going to start looking at the difference between these two. Because when you're working with dependent data, a lot of times you're going to subtract them and see, well, what's changed? So for instance, you can measure a group of kids at the beginning of the year and a group of kids at the end of the year and find out how much did they grow. In that sense, you're going to be looking at mu sub d, which is really going to be equal to mu sub 1 minus mu sub 2. You're going to subtract those things. Let's see what happens when we do just that. Let me subtract from this. I'm going to subtract mu sub 2 on both sides. So we'll take mu sub 1 equals mu sub 2. And I'm going to subtract the right-hand side. I'm going to subtract mu sub 2, just like I have here. That mu sub difference, the average difference, is really the difference in the means here. This is going to simplify. On the left-hand side, mu sub 2, or mu sub 1 minus mu sub 2, that's going to be my average difference. So I'll call that mu sub d. What do I get on the right-hand side? Can anyone simplify that for me?
Would it be 0?
Yeah, thank you. It's going to be 0. So that's one way to test a claim here. Now keep in mind, this claim is the same as that. These are effectively the same. The difference of 0 means that mu1 equals mu2. Thank you, Jillian. Let's try some more here. Let's take a look at this next one. And again, I'm going to subtract mu2 from both sides. So mu1 and mu2. If I subtract mu2 from both sides, let's see what I get this time. Well, kind of like last time, on the left-hand side, I'm going to get mu sub d. And that's going to be less than or equal to 0. Okay. And I think you can kind of see what's going to happen with the last one. Let's do it anyways. So I'm going to start out with mu sub 1 is greater than or equal to mu sub 2. And I'm going to subtract mu sub 2 from both sides. Mu sub 2. And like before, I get mu sub d. This time is greater than or equal to 0. So I end up with 3 different possibilities, but they're the same kind of things that we've been dealing with all along. I can test at the average difference. So mu is the average, d is for difference. The average difference is 0. The average difference is less than 0, or the average difference is greater than 0. But all 3 of these are equivalent to the same kind of test that we did back in section 9.2. Okay, so now what? Well, now we're going to remind ourselves how we did these tests, or how we do our hypothesis tests. So we're going to do the steps in a hypothesis test. I'm hoping that by now these are starting to get pretty familiar, because we've done these for chapter 8 and now chapter 9. Does anyone remember what step 1 has been for us in all these things? What do we always do in step 1?
Define the alternative and null.
There you go. Thank you both. State HO and HA, the null and alternative hypothesis. Cool. Second step. Find alpha. Generally, that's given to you in a problem. If it's not, what are the typical values for alpha that we just assume? What are the ones that we've worked with most often?
0.05.
Yeah, 0.05 and 0.01. Now, the book uses 0.1 from time to time. That seems pretty big to me, but you know, as far as just a textbook example, it's fine. Step 3 for us has been to enter the data. Generally speaking, that's into Statdisk or a graphing calculator. What do we need once we enter the data? What were we trying to find?
The p-value?
The p-value.
Find the p-value. Well done. And once we found the p-value, that allows us to
determine if it's high or low than the
yeah,
alpha.
Excellent. Thank you, Jaleisha. Determine if it's high or low. If the p-value is low, H naught must go.
Go.
So, yes. So reject H naught or fail to reject H naught. So you proved him guilty or you failed to prove him guilty. But we don't say that we proved him innocent, okay? You don't say that we proved H naught is true. We just failed to show that it wasn't true. All right. And finally, step 6, a very important part here, especially because we're letting technology do all our heavy work, is write your conclusion in words. And I'm not going to bother to put it, but it should be words that like the average person can understand so that they can actually look at what your work says and come away with a conclusion that makes sense to them. Don't use stuff like HO or HA or alpha, stuff like that. Just write it in simple sentences. Use the stuff that the author gave you, that wording the conclusion handout that I gave you to help you along the way. All right. Now, there are a couple things specific to this type of test that we're going to have to assume in order to be able to do our test. So let's take a look at the assumptions that are necessary to do test of matched pair data or dependent samples. So our assumptions are as follows. We have dependent samples. Now, typically, that's going to mean matched pairs in some way. Matched pairs. Okay. Then either one of two possibilities. Either both samples are from normal populations, or you have more than 30 pairs of data. The idea here is that one way or another, we want to be able to use a normal distribution. You can, if both your original populations are normally distributed, or when you're calculating averages, and about 30 or more averages tend to have a normal distribution. Okay. How are we looking with that stuff? want to turn our attention to some of the examples. Can I switch screens?
Yep.
Yep.
Thank you. So we'll start with example A. So example A talks about the number of words spoken in a day by each member of 8 randomly selected couples. So it says in part A, use a 1% significance level to test the claim that among couples, males speak fewer words than females. Well, let's give that a shot. So definitely this is paired data. We'd probably have to look and see if this is normally distributed or could be normally distributed in order to finish this. But we're just going to march on with this so that we can practice this hypothesis test. Now, I'll give you a little heads up here. I'm going to pass to you the data, but Statdisk is not very helpful in one respect here with respect to the data. I put in the data the other day and it didn't like it. The reason it didn't like it is because when I put it in, the original data had commas in it. So it had 12,000 and something, and oh, it had a comma. It didn't like that. So if you type in your own data, make sure that it doesn't have commas because Statdisk won't like it. Let me put the data in the chat here for you, so that way you can follow along a little bit easier. Now, some people have had trouble taking the data out of the chat and getting it into Statdisk. My suggestion is that you use Control V once you've copied it to paste it in here. That seemed to solve problems for a couple students in my morning class. My other morning class, I should say. So let me know if that's going in okay. Is it pasting into 2 different columns as opposed to all cramming into one cell?
It worked for me in 2 columns.
Yeah, I got it in 2 columns as well.
Okay. That's what I was hoping for. All right. Good to hear. So let's go back now and work on our null and alternative hypothesis. So we're to test the claim that amongst couples, males speak fewer words in a day than females. Now keep in mind when we're doing tests like this, there's 3 possibilities. You can be testing parameters for mu, sigma, or p. Well, we can probably delete p. The number of words spoken doesn't sound like a proportion to me. So it's not a test about population proportion, nor is it a test about a population standard deviation. It's a test about how much they speak, and it's kind of pushing you towards mu, the average number of words spoken. Now, a little bit more here. We've got 2 different samples, data from males, data from females, but they're the same couples. So that somehow or another, we're thinking that they might be related to each other. Okay. So let me throw out a version of a hypothesis. And it's based on that sentence we have there in green. Test the claim that amongst couples, males speak fewer words than females. Well, I'm going to use mu, and I'll do mu sub m, males, and mu sub f, females. What type of inequality should I put between these 2? Less than, greater than, or equal to?
Less than.
Less than.
Less than. Thank you. Now, because it's a less than, that has to be part of the alternative hypothesis. The null hypothesis would then be kind of the opposite. Mu sub m is greater than or equal to mu sub f. And I like to circle this just to make it easier to look back on. Why do you think I'm circling that? What's interesting about this much?
It's the original
That's the
claim.
original claim.
Yeah, it's the original claim. So that's just so that later on when we're finishing things up and we need to word our conclusion, we can look back and see what our original claim is. Thank you both. Step 2, we need to decide on alpha. And I think in this one, they suggest that we want to use alpha at the 1% significance level. So that's right here towards the beginning. Let me highlight that here in blue. Use a 1% significance level to test the claim, yada, yada, yada. So alpha is 1%. Step 3 for us is the new school where we're just going to put that data into Statdisk or a graphing calculator. And I already sent the data to you, so we put it there. So we're in good shape there. Let's take a look at step 4. What am I looking to get out of step 4? I haven't even run the data yet, but what am I looking to get out of step 4?
The p-value.
The p-value. Wonderful. Thank you so much. So the p-value is going to come when we analyze the data. You want to go to analysis, then hypothesis testing. Which of the ones that I have here am I going to use?
Mean matched pair.
Good. Mean matched pair. So analysis, hypothesis testing, mean matched pair. Thank you, Joe. And I'm just going to write those down here for you. You're looking at the notes at some point. Analysis, hypothesis testing, mean matched pairs. Okay. So let's take a look at this a little bit. Now, these conclusions, or this stuff here, could also be set up a little bit differently. If I were to move this over to the left-hand side so that I'm subtracting mu sub m minus mu sub f, then it's going to give me the difference, male minus female, and my hypothesis is going to look like this. Mu sub d is greater than or equal to 0, and the alternative is that mu sub d is less than 0. So it's an alternative way to think of our hypothesis. It's an equivalent way as long as you're keeping in mind that mu sub d is the difference between those two population means. With that, the alternative is still our, the alternative hypothesis is still our original claim. Let's take a look at which one of these ones I want to pick here for our matched pairs. I got 3 choices, 1, 2, or 3. The mean difference is 0, mean difference is greater than 0, or mean difference is less than 0. Which one do I want?
Less than.
Awesome, thank you. Less than, and let's go up here to alpha, change that to 0.01. Now I think because this is a one-sided interval, the confidence interval that we get is not going to be 1% or 99% confidence level. It's going to be a 98% confidence level. Let's see if that's true. I'm just going to double that. Where was my data? Did I have mine in 1 and 2? I think I had mine in 1 and 2. I'll find out. Okay. Are you getting the same thing?
Yeah.
Mm-hmm. Good deal. Good deal. So that brings me to step 5. What information from this page do I want to put down in step 5?
The p-value, And alpha.
Yeah, we want the p-value. And you're right, we got alpha as well. So the p-value is 0.3295. And how's that going to compare to alpha? So let me write those two things down.
It's greater.
So from Statdisk, we get a p-value, which is 32915. So our p-value is greater than alpha. What's that say about our null hypothesis? Do we object
Fail to
or
reject.
fail to reject? Yeah. Fail to reject. And I'd be happiest if you said H naught, because sometimes people fail to reject the alternative hypothesis or the null hypothesis. I want to make sure you know which one you're failing to reject. Cool. Let's go to our handout on wording the conclusion then. Got that one here. And let me start us with a clean slate. Does the original claim contain the condition of equality? So that's right up here. Did our original claim contain the condition of equality?
No.
No.
No. So that brings us down here on this branch. Did we reject our original claim? Maybe. No, did we reject H naught? I'm sorry.
No.
No, we did not. So that leads us to D. There's not sufficient sample evidence to support the claim that, and then we're gonna have to put our original claim in words. But let me copy this down first. Step 5, actually step 6, I should say. There is not sufficient sample evidence to support the claim that amongst couples, males speak fewer words in a day than females. If you're wondering where I got the rest of that, it's right there. It's what they're asking you to test. Test the claim that amongst couples, males speak fewer words in a day than females. So. There is not sufficient evidence, and let's put in the word sample as well. Sufficient sample evidence to support the claim that among couples, males speak fewer words in a day than females. Okay, looks good there. How are we with that first one? Is that one okay?
Yep, looks good.
All right. Thank you.
I have a question about the mu D. Actually use the data to subtract mu from mu 2.
So there's a different way we can do this test. It would be equivalent. And let me see if I can't find the data here. I think I shared this link with you earlier today. If you wanted to look at it, you could. But here's, let's see, no, I don't have it there. Well, here's some other data that we'll work with in a little bit. What you could do, once you have these two columns, is subtract them. Say the left minus the right, D minus E. And that difference is in column F. So you've taken two columns worth of data, you've got 16 observations. Once you subtract them, you got half that much, you got 8 observations. So basically your degrees of freedom has gone from 15 down to 7. So you're losing a lot, but this is actually a very powerful test because if you have matched pairs of data, there's not much difference between the before and after. So any difference you see can probably be attributed to whatever effect you're looking at, as you're looking at people's body temperatures in the morning and in the evening, or their score on a test before the practice course and then after the practice course. You know, those things, you're controlling for a lot of variables. So it's a really good way to investigate the difference in two means. It's just you can't always set up matched pairs like this. But to get back to your question, I can do a simple t-test of whether or not this is 0. And that'd be essentially what your Statdisk is doing for these two columns, is testing this one equal to 0. Okay, so good question. And I hope the answer didn't get too long, that you're able to still see it.
Thank you, I got it.
All right, good deal, good deal. Now, I don't think I need to bother asking this class because I did a poll in my morning class and I asked who's on social media and it was 100%. So social media is everywhere, including for yours truly, although some of the types of social media that I do are not what most people do. One of them is to log my workouts. And just like Facebook, where you get likes on my app, I get kudos. And until this morning, there was something that I suspected, but never really tested. That was that when I do a swim workout, when I post a swim workout, I don't get as many likes as I do when I post a biking workout. And I don't know what it is. Are my biking friends snobs? They're like, oh, well, you only swam 5,000 meters, you know, that's nothing. I don't get it, but here's the data. And let me share that with you. Actually, I could share it with you in a couple ways and just put that in the chat. So here's the data. We'll put that in the chat. All right. So we'll do a test. And my theory is that the average number of likes I get swimming is less than the average number of likes I get biking. So we'll test that claim. Let's see here. There we go. So we'll call this example B. Test the claim that the average number of, technically they're called kudos, is less for biking or less for swimming than it is for running. Now, I should mention a little bit about how I collected that data, because in this section in particular, there's an assumption about our data. And what is that assumption? What's the big important assumption that distinguishes the test in this section from the test in the last section? Because both of them are testing claims about population means.
This is dependent data? It's from like
Excellent.
The same set?
Yeah, it's dependent data. And what I did in collecting this data is I looked for a day in which I did a swim, and then the next day I did a bike, so that they're right next to each other. So that, you know, if it's a part of the year where people are going to be really busy, maybe I don't get as many likes. So I'm trying to control for as many things as possible. And of course, it's my followers that are putting up the likes. So the data is here is dependent. It's just my data from one day to the next. So I try to make it as dependent as possible. An example of independent data would be if I looked at my likes for swimming versus my buddy's likes for biking. Those would be independent sets of data. So in any case, we've got dependent data. We probably should take the time to look and see that it's normally distributed because I don't have a large enough sample size, but I'm not going to take that time here. Let's run through our different tests or the different steps of our test. The first one is to state our null and alternative hypothesis, HO and HA. Now I ask you to test a claim that the average number of kudos is less for swimming than it is for biking. Let's do it like this. Mu sub S is less for swimming than it is for biking. What does that leave there for the null hypothesis?
Mu sub S is greater than or equal to? Mu sub B.
Perfect. Mu sub S is greater than or equal to mu sub B. Now, if you rearrange these, if I subtract swimming minus biking, let's do mu sub D equals mu sub S minus mu sub B. Then equivalently, this is going to be mu sub D is greater than or equal to 0, and mu sub D is less than 0. The alternative hypothesis. And that's really the way this is set up, is to test this. It's equivalent to testing this. Now, I didn't really state a level for alpha here. So what level for alpha should we use?
0.05.
0.5? Yeah, that sounds good. 2. Alpha equals 0.05. Someone in my morning class wanted to use alpha as 0.1. The value of alpha is going to determine how likely you are to make a type 1 error. So if that risk is really crucial to you, then you use a smaller value for alpha. If it's not, no big deal. Step 3, we should input our data. I'm hoping that that data got to you and you can paste it into Statdisk. So there's Statdisk. If you click the Statdisk online, you should see your sample editor. And I have my data in columns 5 and 6. So step 3, we're all set. Input the data. Now what? What's step 4 asking us to do? Remember?
Find the p-value.
Awesome. Find the p-value. Okay. So for that, go to analysis, hypothesis testing, mean matched pairs. Now your data might be in different columns than mine, that's okay. The first thing we want to set up is the alternative hypothesis. I've got 3 possibilities here, 1, 2, and 3, not equal to 0, greater than 0, less than 0. Which one do I want? 1, 2, or 3?
3?
Yeah, 3. Want the mean difference is less than 0? We're going to do it at the 5% significance level, so I don't need to change that. My columns are in 5 and 6. Bam. Let's take a look at what that's saying. What's the information that I need to get off this page?
P-value?
Yeah, the p-value. And the p-value is 0.00035. So kind of on the small side. Can someone finish this sentence for me? If the p-value is low,
let it go.
Let it go. And that it is the null hypothesis. We're going to reject H naught. Thank you, Soren. So since the p-value is less than alpha, reject H naught. So here's our p-value, and here's our alpha. So the p-value is less than alpha, so you reject H naught. And finally, we want to state the conclusion in words. Step 6. Now, I didn't take note of it at the time. I guess I got to go back and figure out now. Which one of these was my original claim?
H naught. Is it the second one?
Is less than swimming, is less for swimming than it is for biking. Does that have the possibility of equality in it?
No.
So if it doesn't, then which one would it be?
Alternative.
Yes, well done, thank you. So the alternative is our original claim. And that'd be true even over here. And we need that, and thank you for your help. We need that to word our hypothesis, or word the conclusion, I should say. So let me erase these. We'll start all over. Does the original claim contain the condition of equality?
No.
No, it doesn't. Did we reject H naught?
Yes.
Yep. So that puts us at C. The sample data support the claim that the average number of kudos is less for swimming than it is for biking. So let's just state that. Sample data support the claim that the average number of kudos is less for swimming than it is for biking. Yay, sort of. I don't know. I don't know why I guess my friends on my app are kind of biking snobs or something like that. They must look at it, oh, that was a swim day. No kudos for you. It's just funny. It kind of strikes me as odd. But kind of a frivolous example. Thanks for putting up with it. But are you getting out of this what we need to, which is understanding how to do these hypothesis tests? So the plan is to do one more example like this, and then I'll split you up into groups and you can prepare for your exam this Tuesday. All right. Now, a lot of times what leads to matched pairs kind of data is a before and after test. So let's see, is that example C here? Yes. Now this one isn't necessarily stated quite as a hypothesis test. That's okay. We are going to treat this and do this as a hypothesis test. So a study was conducted to measure the effectiveness of hypnotism in reducing pain. The measurements are in centimeters on a pain scale before and after hypnosis. So this before and after stuff helps you attribute any difference that you see to the treatment that was given. In this case, hypnotism. So if there's a difference, it's strong evidence that hypnotism works. Assume that the paired sample data are simple random samples and the differences have a distribution that is approximately normal. That's what we need. That's basically the same assumption we were making with our previous set of data, is that somehow or another we've got a normal distribution to work with. Now they want us to construct a 95% confidence interval for the mean before minus after. So, you know, all right, we can do that. But mostly what I want to do is I want to test a hypothesis. Does hypnotism appear to be effective in reducing pain? If hypnotism is effective, then what should be the case with my before and after scores? How should they compare? What
the
happens
after
if
score should be lower?
Ah, well done. Thank you, Alec. The after score should be lower. So that means mu sub before should be greater than mu sub after. Now, you could also write that equivalently as mu sub after is less than mu sub before, but I want to put my data in this form, before and then after, because Statdisk seems to subtract your left column minus your right column. So I want to get this done in the right order, because as we see up here, they want you to subtract before minus after. So if I put them in my left and right columns like that, it should be good. Let me see if I can't get you the data, then we'll get things set up. Okay, so here's our data. And I think I mentioned earlier that if I wanted to, I could just run a one sample test on the differences. That'd be fine. That would work okay. Let me put that in the chat. Let me know if that comes through okay. Can you paste it into two different columns? So once you get the data, you can go to Statdisk online in the upper left-hand corner. That'll take you back to your sample editor. I've got my data in columns 3 and 4. You can put your data in column 1 if you'd like. May have mentioned it, but I'll mention it again. When you're entering data like we have in columns 1 and 2, you can't use commas, which is annoying because I did a copy, cut, and paste from the book, at least from my math lab, and the number 16,003, for instance, had a comma after the 16, and Statdisk didn't like it. It spit it back at me. So I had to edit the data the other night and take out all the commas. So everyone keeping up that you've got the data stashed in your sample editor?
Yep.
Thank you. Let's catch up with things in terms of our null and alternative hypothesis, that kind of stuff. So, example C. We had HO and HA. We were asked to test the claim that hypnotism actually worked. And I forget who, but somebody helped me translate that into the before scores have to be greater than the after scores. The after scores, once you got the treatment, oh, there's not as much pain. Oh, that's wonderful. The flip side of that is that the before scores are at most or less than or equal to the after scores. That's going to be our null hypothesis. Because this data is matched pairs, we are going to subtract these. And the problem said that it wanted to subtract them in this order, mu sub b minus mu sub a. If I did that here, subtracted mu sub a on both sides, I'd end up with this on the left-hand side. So we'll call that mu sub d is less than or equal to 0. And the alternative would be mu sub d is greater than 0. So that's our step 1. Step 2 is decide on alpha. And they talked about a 95% confidence level, which would correspond to alpha's 0.05. Oops. Step 3, input the data. Got that done. Which brings me to step 4. What has to happen at step 4?
You have to find a p-value.
Yeah, I need to find the p-value. Thank you. So let's look back here. I don't think I've run my test yet. Analysis, hypothesis testing, mean matched pairs. Mean difference is greater than 0, so that'd be the second of these. My data is in columns 3 and 4 respectively. And I get a p-value of 0.24. So that puts me over in step 5. So down here, there's our p-value. Let's go over to step 5. What's going to happen with step 5?
Failed to reject.
Failed to reject.
All right, so I'm not sure I heard a complete consensus. Reject and fail to reject.
Fail.
P-value, go ahead.
I was just saying fail to reject.
Yeah, fail to reject. The p-value is greater than alpha. So if the p-value is high, H naught will fly. We're going to let it go. We're going to not reject H naught. So let things stand there. And that takes us to step 6. And thanks for your help with that conclusion. So step 6, let's get back to wording a hypothesis conclusion. Let me just erase those real quick. Why not? There we go. Let's see. And I forgot to circle something. What did I forget to circle?
Original claim.
Original claim. The original claim is that hypnotism works, which is why your after pain is less than your before pain. Or that the difference of before minus after is greater than 0. It's positive. So, okay. Did the data hold that up though? Did it support our alternative hypothesis? Let's see. Original claim does not contain the condition of equality. So I'll tick off this branch. Did we reject H naught?
No.
No. So that brings us down here. There's not sufficient sample evidence to support the claim that hypnosis appears to be effective in reducing pain is one way you can state things. You could state things a little bit more exact with respect to the test we did by stating that the mean difference of before minus after is greater than 0. So there's a couple ways you can state that. I think I'd be comfortable with both of them. So there is not sufficient evidence to support the claim that the mean difference before minus after is greater than 0. Like I said, an alternative to that, let's see, that. You could finish things up with hypnosis appears to be effective in reducing pain. Okay, so you could either use what I have in brackets or what I have below in red. Both of them would be fine. Awesome. Comments or thoughts on this last one here? I hope you're feeling more comfortable with this kind of stuff, because this is the kind of things you're going to have to go through on an exam. Certainly, at the very least, the final. Well, we've also got a test coming up this Tuesday. So good luck with it.